the washer method. It is only the washer method if you're from Ohio. The rest of us call it washer. So the washer method. The difference between this and the disk method is that the rectangle will not be sitting on the axis of revolution. Okay? So when you rotate the rectangle around, instead of getting a cylinder, you get a cylinder that's hollowed out in the center of it. Called a washer. Okay? All right, so that's what we're going to be dealing with. So now think about it. Instead of just having one radius, we have two. Because we're going to we could take the volume as if the hole was filled in the middle. Then we have to subtract out the volume of the hole. Okay? So we'll have an outer radius that goes from the axis of revolution to the far edge of the rectangle, and we'll have an inner radius that goes from the axis of revolution to the near edge of the rectangle. The outer radius gives us the volume as if the whole thing were filled in, and then using the inner radius, we get the volume of the hole, and that's what we subtract out. Make sense? Okay. It's going to be a little more complicated. Yeah. Okay. But it's the same basic idea. So let's see. I'll let that one continue to twirl. All right, so can you imagine what that one's going to look like when we take it about that axis? You got an idea of what you're going to see? It's going to go across that horizontal one, I think, or around the horizontal one. Oh, we went the other way. Yeah, that's going to be a challenge, isn't it? Oh my goodness, they're going backwards. Cool, huh? That's the figure you start with. Then here's the idea. You pretend it's all filled in. You take out the hollow part. There you go. Okay, so when the axis of revolution is not adjacent to the end of the rectangle, a washer, which is a disc with a hole in it, is formed. To find the volume of the washer, find the volume as if it were a disc, then subtract the volume of the hole. So we've got pi, and then capital R stands for the outer radius squared dx, minus pi, little r stands for the inner radius squared dx. So that's the volume of the, think of it as a big cylinder, little cylinder, right? The little cylinder being the hole, the hollow part that needs to be subtracted out. Now, you know how integrals work. Instead of taking the integral of that one minus the integral of that one, can't we combine that into one integral? Okay? So we can make it the integral of pi outer radius squared dx minus pi inner radius squared dx. And look how I wrote those radii. If we have a horizontal axis of revolution, those radii, I mean, they might be a constant, but don't count on it, right? They're going to be some expression of x. They're going to be functions of x if it's a horizontal axis of revolution. Okay? And then, like we did yesterday, you might as well factor the pi out and put it in front. So, again, like we did yesterday, you're going to need to draw the region. You're going to need to draw in a rectangle. You need to figure out the width of the rectangle, because the width of the rectangle, the dy or the dx, determines which variable should be in your integral. Okay? The dy or the dx is the height of the washer, the cylinder, the disc. Okay? So it's got to be there, and then all your other variables have to match it. Sometimes they're the same each way. I'd have to look at that one again. I don't know. Sometimes they are, but that's pretty rare. But what you might have to do, is you might have to piece things together, because there might be part of the region where your rectangle would actually form a disc, and part of it where it forms a washer. So you'll have to work two separate problems and then add them together at the end. See what I'm talking about? Okay, so that's probably what would have happened on that. All right. So what I just highlighted in yellow, I think you need in your notes. So if you have a horizontal axis of revolution, the volume equals pi times the integral from a to b of the outer radius as a function of x squared minus the inner radius as a function of x squared dx. And then the vertical axis of revolution, everything shifts to y. Volume equals pi times the integral from c to d. Those would be y coordinates now, not x coordinates, of the outer radius as a function of y squared minus the inner radius as a function of y squared dy. While you're writing, I'll mention this because I didn't say it here. When I went from this line to this line, not only did I factor a pi out and put it in front, I also factored a dx out and put it in the back, didn't I? And then here at the bottom of the page, radii usually involve y equals f of x or x equals h of y. I just didn't want to use f again. Graph the functions, draw a rectangle, find your limits of integration. I should have written in find dx or dy, label dx or dy, find the radii. That's usually the hardest part. Usually. Solve the integral. And look, we've dealt with integrals quite a bit now. They can give us integral, they can make the problem almost impossible to work, right? Give you a couple of functions that are really, really difficult to integrate, give you some limits of integration that are impossible to substitute in and get anything that looks like a normal looking number. They can do that. They don't. For the most part, the integration should be the easiest part of the problem. Now, should be and actual being that way are not the same thing. But for the most part, they give us functions that we can integrate. They give us numbers that we can substitute in. Okay, that doesn't mean it's going to be easy. I mean, you may have to find the sine of pi over 4. Okay, you may have radicals in your answer and this and that. But getting to the integral is the big issue. That's the new stuff. We're supposed to be able to solve the integral. Okay? All right, any questions before we move on? Okay, so that's just the stuff I showed you in the animation. There's the stuff from the book, if you want to take a look in the book. There's that one. And here's this one. And they broke it up into two pieces. It's disk from 0 to 1 on the y-axis, and then it's a washer from 1 to 2. So you would set up two different integrals down here, get each volume, add those together. Okay? And there's that one where they showed us taking the plug out of the middle. And let's go to number 11. You worked part of number 11 yesterday as an example. Now we're going to do 11 part B. So the directions still say, find the volume of the solid generated by revolving the region bounded by the graphs of the equations about the given lines. This time, though, the axis of revolution turns this thing into a washer instead of into a disk. So we graph, and I'll show you doing it over here. We got your coordinate plane. So graph y equals the square root of x, something like that. Graph y equals 0, I already have, that's the x-axis. Graph x equals 4, x equals 4. And the axis of revolution is the y-axis. So look, I'm going to erase some of my graphs. I don't really need that hanging over. Don't really need that hanging over, right? So that's the graph of y equals the square root of x. We're taking this thing about the y-axis. So we've graphed it. I see my region. But like I told you yesterday, the axis is important, and that's the reason I want you to write that down, because if I took this about the x-axis, I'd get a disk, wouldn't I? But I'm going about the y-axis. So your rectangle still has to be perpendicular to your axis of revolution. So your rectangle needs to look something like that. And that's when you realize, okay, the dx or the dy, it's dy. Okay, the width of that rectangle, which is the height of the washer, is dy. And that ought to be clicking in your head to think that means everything is in terms of y. So my y equals square root of x, awesome, and also useless, except to turn it into x equals y squared. I've got to have it as a function of y, okay? And it's kind of weird. Function of y means it's got to be solved for x, okay? Just like our normal functions that are functions of x, they're always solved for y, aren't they? So function of y means solved for x, okay? And we've got to start doing this now. We need to tell whether or not we have a disk or a washer. Because, I mean, if you try the wrong technique, if you think you've got a disk when you really have a washer, you're not going to subtract out the whole, and you're going to obviously get the wrong volume. So at this point, you've got to decide, hey, when that goes around the y-axis, that makes a washer. Okay? Everybody with me so far? Okay. So, volume equals. Now, remember it's the volume as if it were solid completely through minus the volume of the whole. But then we factored out a pi and put it in front. And when I worked it out, it was a dx that I factored out and put in the back. In this case, it's going to be a dy in the back. So we've got to figure out what goes in there. And it's outer radius as a function of y, in this case, squared, minus inner radius as a function of y squared. Okay? And the reason it's just that in there is because let me back up. Pi r squared h. That's what we're dealing with, right? That's the volume of a cylinder. So the pi we've already taken care of right there. The h we've already taken care of right there. So it's just the r squareds that we have to worry about subtracting. You with me? Okay, so the outer radius starts at the axis of revolution. So it starts here, goes to the far edge of the rectangle. And you know how I've always said it's not a constant? It could be, but it hardly ever is. This one is. Because whether it's that rectangle or one down here or one up here, that outer radius is always 4, isn't it? Because it goes all the way to the vertical line, x equals 4. So the outer radius is 4. And what do we have to do to it? Square it. After we square it, what do we do to it? Subtract the inner radius. Minus. Now, the inner radius starts here, goes to the near edge of the rectangle. Now, I'd like to just say that that distance is whatever that x-coordinate is. And I'm correct, it is whatever that x-coordinate is. But I can't put x, because then I'd have x's and my dy's, and that's just crazy talk. Okay? So instead, what does x equal? Y squared. So the inner radius is y squared. What do I have to do to it? Square it. And on a problem like that, where you already have an exponent of 2, guess what people forget to do a lot of times? Put the other exponent of 2. They forget to square it. It looks like it's already been squared. Okay? And that is the integral we have to solve. Oh, wait, I forgot something. Limits of integration. All right. What's the lower limit of integration? What's that y-coordinate right there? 0. Then what's the upper limit of integration? What's that y-coordinate right there? 2. Now, we had some trouble with why that was 2 when we worked this yesterday. It's 2 because there's the point of intersection of x equals 4 and y equals the square root of x, right? When x equals 4, what does y equal? 2. So that's how I know that y-coordinate is 2, okay? So it's the integral from 0 to 2. Now do we have everything we need? Yeah, that's it. So volume equals pi times the integral from 0 to 2 of the outer radius, which is 4 squared, minus the inner radius, which is y squared, squared dy. Now, a mistake that I know you won't make is you won't do 4 minus y squared in a parentheses and put a square outside that, will you? There's a difference between squaring the 4 and squaring the y squared as opposed to making it a quantity and putting an exponent of 2 on there. So don't make that mistake. All right, so this starts off pretty easy. That becomes pi times the integral from 0 to 2 of 16 minus y to the 4th dy. It's still pretty easy. I know what the antiderivative of 16 is. What is it? 16y. And what's the antiderivative of y to the 4th? 1/5 y to the 5th. And it's got to be negative because there's a negative sign there. So volume equals pi times 16y minus 1/5 y to the 5th, evaluated from 0 to 2. So we start evaluating. Evaluate for 2 first. So volume equals pi times. When you evaluate for 2, 16 times 2 is 32. And then negative 1/5 y to the 5th. Well, 2 to the 5th is 32, so negative 32 fifths. Put a minus sign. Then you evaluate for 0. Well, you get 0, don't you? You get 0 minus 0, which is 0. All right, go ahead and do this on your calculator. And 32 minus 32 fifths turns out to be 128 fifths. So most often we write that as 128 pi over 5. Well, that seemed less than horrible. Questions? Now, I'm also not going to try to claim that's the easiest thing you've ever done. Once we got the integral, once we're here, it should be, you know, as far as the calculus class is concerned, relatively easy. But remember, in calculus, relatively easy doesn't mean easy. Okay? It means challenging in any other class. That's right. But we can do that. Okay? We can do that. All right, let's try another one. Oh, it's still number 11. At least I know what the graph's going to look like. This time, the only thing that changed is the axis of revolution is now the line x equals 6. It is, isn't it? All right, so we know that. We even know that that's a 0 and that's a 2. That's an x equals 4. I don't know why I made that so long. But what I don't have on my graph yet is the axis of revolution, which is x equals 6. All right, you with me so far on the graph? And I really do draw a different graph for part A, part B, part C, part D, because it's always a different figure. It's a different solid every time. Okay, because they change the axis of revolution. So it's a different figure every time. All right, the rectangle needs to be perpendicular to the axis of revolution. So that's a dy again, isn't it? dy. So everything's got to be in terms of y. So instead of labeling my y equals square root of x, I now know to call that x equals y squared. Okay? And is this going to be a disc or a washer? Fairly obvious, going to be a washer. There's a big gap there. It's going to have to be a washer. Okay? So we need to find the radii, don't we? Okay? Do you want to go ahead and get what we can get set up of the integral? All right, so volume equals pi out in front times the integral from what to what? 0 to 2 again, because those are the boundaries, those are the y-coordinate boundaries of our region. 0 to 2, put a bracket, in the bracket, dy goes back here. So we can get that far. Now, outer radius squared minus inner radius squared. Outer radius. The radius starts at the axis of revolution. The outer radius then goes all the way to the far edge of that rectangle. Since our axis of revolution is not the x-axis, not the y-axis, that's when we tend to have to subtract to find the length of a radius. So think about it the way we did yesterday. If we started here and went all the way over to the y-axis, what would that length be? Be 6, wouldn't it? Okay? So, 6. But I've got to subtract out that distance right there, don't I? Because the radius doesn't go that far. So it would be 6, but then we have to subtract part of it out. Well, what is that little purple distance? It's whatever the x-coordinate is, right? If the x-coordinate's 2, it's a 2. If the x-coordinate's 3, it's a 3. But I can't put x because that messes with my dy, so I put what x equals. What does x equal? So the outer radius is 6 minus y squared. Then I got a square. Outer radius squared. So I found the outer radius. It's 6 minus y squared. Then I squared. Now, let's stop there for a moment. Because I've been doing this for a while. And that tends to get people. Are there any questions on how I came up with that outer radius? All right. When you're doing these problems on your own, don't be afraid to stop and think, because that'll get you guys are smart. Stopping and thinking will get you a long way. It can be lower. That doesn't change anything, because the outer radius still starts here and goes to here. So if I went all the way from here to here, that would still be 6, but I still have to subtract out that. And what is that distance? It's still whatever the x-coordinate would be at that point. And that x-coordinate, I'd love to be able to put an x right there, but it screws that up, doesn't it? So since I can't put an x right there, I put what x equals, which is y squared. Okay? Does that help everybody? I saw a few people nodding. That must have helped. Okay? Uh-huh. Let's not. Let me finish this one. Okay? That's outer radius squared. We good? Minus. Okay, I'm running out of colors. The inner radius starts at the axis of revolution, goes to the closest edge of the rectangle, the near edge. What's that distance? 2. But I got it by subtracting. 6 minus 4. So I still had to subtract. Since my axis of revolution wasn't the x-axis or the y-axis, I still had to subtract to get it. It's just that I got a constant this time. Instead of 6 minus y squared, it's 6 minus 4. What do I have to do to that? Squared. You with me? Okay. So, that's our volume. Pi times the integral from 0 to 2 of 6 minus y squared, quantity squared, minus 2 squared. So we square that binomial, so volume equals pi times the integral from 0 to 2 of 36 minus 12y squared plus y to the 4th. And then I hope you know that 2 squared is 4, so a minus 4 at the end. And before you start integrating, combine that 36 and that negative 4. And I also reordered. I like it better when the big exponent's in the front. I mean, there's no rule that says you have to, because you're just going to stick numbers in. But that's the way I like it. That's the way I did it. So I've got the volume equals pi times the integral from 0 to 2 of y to the 4th minus 12y squared plus 32 dy. And remember that the pi is important and the dy is too. It doesn't actually affect the outcome of our answer at this point. But when we figured out the dy, that's what let us know everything was in terms of y. Okay? So way back when we first started doing antiderivatives and we just stuck a dx on the end because I told you to, turns out that's somewhat of a big deal. Okay? I couldn't explain that to you at the time. You didn't know enough. But now, I mean, the dx, or in this case the dy at the end, is sort of a big deal. It's got to be there. It's got to match up with the variables of everything else in there. All right, so we get pi times then 1/5 y to the 5th minus 4y cubed plus 32y. Fortunately, when we evaluate for 0, we get a 0, so that means really all we got to do is worry about evaluating for the 2. So that's pi on the outside still, 32/5 minus 32 plus 64. And evaluate for y, but it's a 0. And so use your calculator to turn all that into a fraction. You get 192 over 5. So times pi, we get 192 pi over 5. Any questions? What chunk? Yeah, that is that. Okay, does that make sense? Because this is outer radius squared minus inner radius squared. Okay? All right, I want to talk about this for just a second because it was brought up. And if it doesn't make sense, I want to move on. We've got that. Same thing we've been dealing with. Okay? And our axis of revolution is over here. What would the outer radius be? Be 6, wouldn't it? Because from -2 to 0 is 2, and then plus 4 more. The outer radius would be 6. It'd be a constant. 6. What would the inner radius be? All right? Because here's a distance of 2, and then that other little distance is x. Y squared. Y squared plus 2. Okay? All right. Last example for today. Number 12, part C. All right, we've got y equals 2x squared, y equals 0, x equals 2. The line y equals 8 is our axis of revolution. So, here's what I do. Y equals 2x squared looks like this. Y equals 0 is the x-axis. X equals 2 is a vertical line. The line y equals 8. Now, I got to do some figuring here because is it up here? Is it through here? Is it down here? Right? I need to know, don't I? It makes a difference. It makes a big difference. All right, so let's do some thinking here. Here where x equals 2. If this is the graph of y equals 2x squared right there, then this point right here is 2, and then whatever 2x squared is. Well, if x is 2, 2 squared is 4, 2 times 4, 8. So that's where the y-coordinate 8 is. Goes here. Yeah, see, I needed to know. I needed to know what that y-coordinate was at the tip of my region because I needed to know where y equals 8 went. Above it, below it, or through it. It goes through it. That's probably good. Okay? Not necessarily, but probably. All right. Everybody with me? So I've done a lot of thinking already. Now I need to draw, so I need to write down about the line y equals 8. Let's draw in a rectangle perpendicular to y equals 8. So it's got to be that way. What's the width of that? dx or dy? dx. So we're back to x's. dx. Does that give us a washer or a disk? Washer. All right, you want to go ahead and let's start this thing. Volume equals pi times the integral of, and Okay, hang on. Let me do the end. Dx. So I know my limits of integration are in terms of x because of the dx. So not 0 to 8, that's the y coordinate. 0 to 2, those are the x coordinate boundaries. 0 to 2. We good? All right, outer radius. So the outer radius starts at the axis of revolution, starts at that line, y equals 8, goes to the far edge of the rectangle. No matter where I draw that rectangle, that outer radius goes all the way down to the x-axis, doesn't it? So it has a length of 8. So 8 squared, outer radius squared, 8 squared. The outer radius is 8, outer radius squared is 8 squared. Minus the inner radius. The inner radius starts here at the same place, at the line y equals 8, but it stops at the near edge. Okay? That near edge is at y equals 2x squared. So let me redraw it. Let me draw it so it actually hits the rectangle right there. Okay? So what's the distance of that green segment? Well, if it went all the way down to the x-axis, it would have a length of 8. But it doesn't. 8 minus 2x squared. Because we got to subtract out that distance. It's a vertical distance. So we got to subtract out whatever that y equals. And that y equals 2x squared. So the inner radius is 8 minus 2x squared. It's 8 minus y. Right? It's 8 all the way down minus that y coordinate. But I can't put y because that messes with the dx. So I put what y equals, 2x squared. What are you talking about, upper left? Okay. Right. The green stuff there is the 8 minus 2x squared.
That's not something.
No. Here's the solid part. All right, everybody see the region we're looking at? All right. Not the blue region. That's the hollow part. The blue region's the hollow part. Is that blue? The blue is the hollow part. The yellow region is our solid. Okay? All right. Go for it. See what happens. All right, if you're watching the video, you need to hit pause when you finish that problem because I'm going to put the assignment up here. And now if you're watching on video, I wish I could tell you to unpause. So your assignments, page 463, 5, 6, 11, 12, 13, 14.